All right. So, welcome to this new edition of Engineering Trainer TV. My name is Luuk. I'm the CEO of engineeringtrainer.com, and I'm really happy to have this new stream, the second stream that we will have with Geronimo Zamora Garcia. Geronimo is a pipe stress expert and pipe support expert. He has a ton of experience working with large EPC projects, a ton of experience working with process piping. Um, this live stream is related to a free pipe stress foundations module that we have on engineeringtrainer.com. And thanks to the effort of Geronimo, it's actually now available in Spanish as well. So, Geronimo, it's a pleasure to have you on board again for this second stream that you are joining. How is your day going so far?
Yes, working a lot to be honest. But it's good. It's good. It's doing great. I mean, thanks again for having me here, man. It's a blast as always. So, and in
Exactly.
particular to have this excellent topic today.
Yeah.
And let me just allow me to thank you so much for giving me this opportunity to put this amazing content in Spanish, my native language, to be, let's say, accessible for people like who speak Spanish but don't have access to learn to speak English or doesn't know how
Yeah.
to speak English. So thank you so much.
No, yeah, I mean we're happy to have you and release this product in Spanish, obviously, and see if we can help those engineers out. Next to Geronimo, I would also like to welcome everybody that is watching the stream. And as always, that's very important to us. If you're watching this, please join the chat. So let us know this very instance. Open the chat and let us know from where in the world you are joining this stream. It's always good to connect and see who's out there. Um, Ask questions and interact with us. So, Kevin, hey, from the Netherlands, awesome to have you on board. And as always, if this type of content is relevant for you, check out the YouTube channel, obviously, our LinkedIn company page of engineeringtrainer.com, and connect with either me or Geronimo directly on LinkedIn just to start a conversation. I mean, we love to just reach out and see what's going on. We'll roughly take 30 minutes for this stream, depending on questions and discussions, but that's the aim. Yeah, well, Geronimo, maybe it's a good thing to kick things off and tell us a little bit about yourself and from where are you tuning in, for example.
Excellent, thank you. Well, again, this I'm mechanical engineer by profession. I have a master's degree in mechanical engineering of process plants. I currently work for TR, one of the biggest companies, EPC companies in Europe. In Europe, I would say
Right.
the biggest. I don't know. That will be at least one of the
I wouldn't
biggest
know,
ones.
yeah.
Yeah. And currently, I'm again like pipe stress. The global piping stress manager deputy. So I'm right hands with the global manager, and I do so many interesting stuff that I'm really grateful for. Yeah. So like developing projects around the world, and like I mean, let's say charge also for training activities. Doing a little bit of quality control, quality assurance within our line of work. Also
Nice.
assessing, yeah, and also have but the greatest opportunity to almost every single crazy calculation gets into my hand. So over the years it will
Is that a nice thing, or is it
yeah, it's a perfect, depending on your point of view of things. To me, I'm really grateful for, because it allowed me during these years to expand my knowledge as crazy, which is
yeah,
always good. So every single, thankfully, I would say thankfully, depending on your perspective on how you see things. But to me, it's been a blessing, because let's say every single, or almost every single complex calculation, it's being brought to the department, and then it's being assessed by a
yeah,
team of two, which is basically my boss and myself. So it's super interesting, and
yeah,
and yeah,
that's a good
that
platform to
basically
become a
sums it
specialist. Yeah.
up. Yeah. All
Nice.
right.
So, just to reach out to the audience, I mean, Preston, thanks for joining for joining from Nigeria. Aylin, thanks for joining from Switzerland. We have Mohammed from Egypt on board. John Santos from South Korea. I mean, it's a very international crowd again, which I always
Welcome.
find amazing. So yeah, let me just share my screen. Give me a second to update the stream. Because typically during these live sessions, during these Engineering Trainer TV streams, I interview one of the specialists, one of the instructors for the courses. In this occasion, we actually are discussing a course that I myself made in the beginning, and that Geronimo now translated. So it's this course that is shown on the screen at the moment, Pipe Stress Foundation, which is a 1.5 hour free module, training module on the engineeringtrainer.com platform. So make sure to check that out. If you haven't, you can just subscribe, set up your account, and do the course. Yeah, Geronimo, like we collaborated recently to build a Spanish course, shown
Yeah.
here. What's your take on the course? Like, why were you so eager to translate it?
I think we were joking around. So one of the things I would like to highlight in this live session is that it will be a different live session that you're used to, because it will be just a regular conversation between you and me, because you will also be, so you were a participant in developing this course, so it will be
Exactly.
fun because it will be fun because you will be more like actively carrying the thing. So that's one thing. And I remember the first time I saw the content, I was like, I saw it really, really interesting, because I've been working in this thing for the past, I don't know, 15 years, 14 years, whatever. And I know a lot of people, like I have colleagues and friends of mine, that they wouldn't know or understand completely the basically the content of this course,
Right.
which I found really interesting. So when I first saw it, I was like, yeah, this is great. This is super clean, super efficient. Like it's a perfect way to lay out this type of content, and in the way that I really liked it so much. So then, rest is history. I reach out to you, and in my case in particular, let me give you this small, let's say, parenthesis or feedback. Like, I come, as you might know, originally from Venezuela. I come from that's an Spanish speaking country, and
Right.
I can tell you for a fact that there's a lot of people that there and in Latin American countries, which is kind of a weird thing. Like, well, not a weird thing, but not everybody have the opportunity to learn other languages. So you can
Sure.
spend
Yeah.
your life there, and only would you speak your language, which is Spanish. And developing my career there, the first years was kind of I was like, it was really advantageous for me to being able to speak English, to speak the language, and being able to reach out to content that it's mostly in English. So
Yeah.
I was able to expand my knowledge better. So I like doing charity. I like doing things for my community here, there, whatever in the world I am. And I saw it as a great opportunity to put this great content in Spanish, to make it available to this amount of population that basically don't have access to it, or let's say help with this type of content, right?
Exactly. Yeah.
Which
Yeah. Yeah.
from the beginning, I thank you so much for that. Which
No worries, no worries. Like, I'm happy to have you on board.
Great.
All right, let's just dive into the courses. So what we will
Sure.
be doing during this stream is we're gonna actually just do a quick rundown through
Yeah.
the Pipedrive Foundations module, and just have a little bit of discussion about it. I'll start with some presenting. We can go a little bit back and forth. What you see on the
Yep.
screen currently is the course itself, which is available in Spanish as well, as I show here. And what I would like to do is actually take one of the subjects that, to me as an engineer, when I started with the pipe stress discipline, was one of the more difficult topics to grasp. And I think that's also the basic topic of the module. And it is related to if you derive the stress equations for, let's say, a section of pipe under pressure, for example, how do you go from there, those equations, to the equations that you see in the piping codes, right? The ASME B31.3, EN3480. So that's kind of going to be the main topic of the conversation. I'm going to kick things off in just showing you those features a little bit, and then me and Geronimo will go back and forth about it. So in these first videos, as you can see in my screen at the moment, we derive the different stresses that are relevant for a piece of piping. The normal stresses, we have axial, we have radial, we have circumferential, which is basically the axis, or sorry, the orthogonal directions. When we were discussing this, Geronimo, you actually pointed out something about the circumferential direction.
Yes, yes. Well, let me first kind of sum up like this course. Like, I would really like to invite the people to really watch it, either in English or now it's in Spanish, to because it goes from whatever stress theory you might have from a being and take it out to explode it into piping world, right? From the type of stresses you might have there, the stress directions, type of stress, normal stresses, shear stresses. How do you kind of let's say work with those, and how basically at the end of it there's an example how you develop an equation from the code that basically
Exactly.
comes from all this theory that we're developing, which is amazing. So that's why I said I really find it really really interesting. So with the normal stresses, you will have like, okay, actual stress, sorry, and then the circumferential stress that we call hoop stress. We're gonna go back at it in a minute. Radial stress. What do we do with those? The fun fact though, first fun fact will be right, like from this session is why is circumferential stress called or referred as hoop stress? As you
Yeah.
as you might know, to circumferential stress as hoop stress. Why do we call
Yeah.
it hoop
Yeah.
stress?
Yeah.
Yeah, so the terminology comes from the supporting hoops in wooden barrels, actually, hence the name, which is really interesting. So back in the day when this were all developing, they grabbed that and put it in the code in many books. So
But
commonly,
just like wooden barrels, like what is the
yeah,
context of wooden
so
barrels?
so wooden barrels. So commonly wooden slats, which are in the barrels, are held in place by metal hoops, right? Like by
Yeah.
hoops.
Yeah.
Those
Yeah.
hoops are, yeah, so those hoops are used to hold the slats together and provide support from the pressure that pushes them out radially, right? So the
Yeah.
radial force pushes out the putting the metal hoops under hoop stress, hence the name hoop stress. So if you analyze those hoops, metal hoops, they're purely entirely subject to circumferential stress, right?
So you say it as if it makes total sense that there's wooden barrels that have hoops. That has
Yes.
nothing to do with process piping, right? Is that back in the
No,
day of
no.
kind
This,
of
I think,
shipping wine in barrels or something?
yes. I think
Ah,
I think when these were all developing, like back in the 1940s, 50s, 60s, the technology was out there, and they basically say, okay, circumferential stress, and then say, okay, it's hoop stress, right?
it's
Like
the
it's
it's
the
the
same
hoop
thing.
one. Yeah, yeah, yeah.
It's the
That's
hoop
fun.
one. So hence
Yeah,
hence the name though. It's basically the supporting hoops in the wooden barrels.
yeah,
That's
yeah. Oh,
that's
that's
a,
good fun.
that's a
Yeah.
fun fact.
Yeah. So just to dive back to the course, hoop stress, we switch circumferential to hoop, which is displayed here. I won't go into detail about the derivation of the um, associated equations. We'll jump to those in a second. And basically, what right, do you remember what happens every time is you neglect the radial one because it's rather small. We'll show something about that in a second as well. And of course you include shear stress due to torsion because that one can be significant.
Yeah,
Um, so as I said, like the radial stress, it can be is typically neglected for thin walled piping. I've did a quick analysis of those numbers for a nominal DN 500 pipe, standard thickness with a pressure of 10 bars. So you clearly see, let's say, the bottom distribution, this line is the radial stress throughout the wall thickness of the pipe. And then if you jump to axial stress and especially to hoop stress, those numbers are just much higher. And we actually have a different free module, thin versus thick walled piping, available on the platform as well. So, if this kind of stuff is interesting, make sure to check out the free
Yeah.
modules. This one is actually a preview of the pipe stress analysis course, which is going to launch very soon. So could be of interest to you as well. All right, jumping back to
Can you? Yeah,
those.
yeah. So in this slides, it's really interesting too. So we grab the normal stresses that are typically on a beam, and we take that out to a cylinder, basically, right? So
Right.
as normal stresses, you end up having axial stresses, hoop stresses, or circumferential hoop stresses, and then radial stresses, right? Like so, put it in the coordinates of the cylinder, basically.
Yeah. Yeah.
And then those will be normal stresses, and then you would have shear stress, which the main one right here is the one to tend to twist the piping, and is torsional stress, which basically the shear stress present in this field, right? So what it's really interesting, as you were mentioning, is like in thin wall piping, and we're gonna call, because the thin wall piping is a very blurry definition depending on who you ask, all right, or depending on the
Which
code
code
you
you check, which
depending on the code you use. So, for example, B313, it's something crazy. Well, not crazy though. It's thick enough. It's almost, it's not that high, but with the EN code, it's almost the same. So to me, that's a thick pipe. Like it's D over T, higher than six. That D over
yeah,
T
exactly. Yeah.
ratio higher than six. So that's a thick pipe though. But
Yeah.
it's,
Yeah. Yeah.
I mean, like generally speaking. But it's that we're using, let's say, thin wall pipe equations to compute thicknesses there, right? To have
Yeah.
some sort of degree of examples here. So what is interesting is like when you do, because there's a lot of, in the codes, there's a lot of safety factors behind stuff, not only the common safety factors. We're going to talk about it in a minute. But which is really interesting is like, because I have some friends, some colleagues, and people that reach out to me, that says, okay, why do we neglect the radial stress? The radial stress is
Yeah.
present there. Radial stress will be basically your internal pressure at some point, right? So in thin wall piping, you're able to do so because the percentages are low enough for you to consider them like it won't impact your results. But that's upon also, and it's really important to highlight that that's upon also safety factors. So you're able to neglect that because it does simplify the calculations,
Yeah.
right?
Yeah.
Then you're able to do so because the percentage is small, so you're taking care, you're accounting for that. um, you can account to neglect that. All right.
Exactly.
And the other hand, when you're working with thick wall piping, then you say, okay, since thick wall piping will be like super high pressures or high pressure piping, then you say, okay, radial stress is important, so I'm going to put it in my equation. So you might have local, like radial stress might produce local deformation like within the pipe wall and stuff like that. So the approach is completely different, because when it's, what is really important to highlight, if you would use thin wall equation to compute the thickness for a thick wall pipe, for
Yeah.
high pressure, to a pressure that is super high, the results will be in, you might think it will be not conservative, but it will be completely out of proportion conservatism
Yeah.
within that. So yeah, so that brings a little balance within the codes, to be honest.
Interesting. Yeah. Yeah,
Let's
well,
continue.
let's get back to that a little bit in later. Like, we'll discuss like hidden safety factors a little bit.
Yes,
But
we will go back to that one briefly.
so going from this, like when I started, you can, for example, derive these like equations for, let's say, pressure loading, right? Hoop stress, stress is pressure times diameter divided by 2 times the thickness. For the actual stress, it would be divided by 4 times the thickness, and
Yeah.
here the thin walled assumption is already made. So at some point, the derivation, by the way, are in the course itself. But at some point, you'll end up with these type of equation, which are pretty straightforward and are also very well represented in the codes. If you look at the thickness calculations for piping in the ASME, or but also in the EN3480, you'll definitely recognize the basics of this equation. But going from here to, let's say, the actual code stresses, that was something that took me a while, and that's something that we'll do a deep dive into. Maybe a little bit fun fact for everyone watching, Geronimo, for you as well. I know you know the answer. Let's say if the pressure in a piece of piping is increased till the pipe bursts open, in what direction will the crack be? Um, so yeah, what do you think?
Dun, 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 dun. Yeah. So the reasoning behind it is like there's so always let's say like that. So crack, it's always perpendicular to the stress direction, right? Like
Exactly.
it's
Yeah.
yeah. So it will be. That's why in B313 and other codes you use the joint efficiency factor for longitudinal, the longitudinal one, because in hoop stress the pipe will burst this way, which is important when your pipe is not seamless. You need to account for that efficiency longitudinal, right?
Mm, right.
As against as you might
Yeah,
think,
fair
like when
point.
you're computing, that's a fair question. So mostly, there's an interesting topic when working in creep range, where whether if you use the well joint strength reduction factor with the circumferential welding, because you're worrying about
Yeah,
actual stress. So
yeah.
that's up to the designer in that code. But yeah, that will be the explanation for the answer, I think.
Yeah, that's a good answer because you haven't given the exact answer itself. That's nice.
Well,
So the answer obviously is that the crack will be in the axial direction, right? I mean the highest stress component is in the hoop direction, circumferential direction. So the crack will be actually. But I mean this question, it always gives it's good food for thought, in my opinion.
yes, yeah, yeah,
So all right, so then the question becomes, okay, so from these directions, we have axial, hoop in the normal, we have shear, torsion stresses, and then in the other hand, the typical stress strain curves, which is shown here. We have stress on the vertical and strain on the horizontal axis, and this is typically a simplified view of a stress strain curve for, let's say, metal. The elastic region where Hooke's law is applicable. Then we have a yield point, and yielding or plastic deformation takes place until the breaking point. Sorry, the ultimate tensile stress, after which necking occurs and the metal breaks basically.
basically bakes, yes, breaks,
But this is a result from a uniaxial tangent test, right? So you take a piece of
yes,
metal and you just pull it apart and you measure the displacement and you measure the force required to do that displacement, and you'll end up with this graph. But that is in one direction, right? So the question becomes, how do you think about these different stress directions and forces working in the location of metal, and how do you compare it to the yield stress, the ultimate tensile stress?
yes, yes.
And the
So
answer, sorry,
let
yeah,
me just point this out. Like it's super important for beginners that these stress strain curve represents, like you mentioned it, but it's important to highlight it. It's for ductile materials like such as steel.
yeah,
Like
fair
if you
point.
would have rubber or any fragile material, the curve will be completely different, right?
Yeah, I
So
think that's actually, I have
it
like
is in it is in the course though. Yeah,
something
that one.
like this. Like
All
it's
right.
a
Yeah,
very
yeah.
rough, like playful view,
Another
not to scare away beginner.
another
Yeah,
important thing to highlight is with this type of curves, those are not completely in scale for you to have the whole information. So it's always, because you see this type of curves, and it's important to know that those are not completely scaled up to a single measurement scale, but
yeah,
are basically compressed by different factors there in it for you to have an understanding where the key areas are, right? Like your
yeah,
elastic region, your plastic region, necking, and yeah. So as you were mentioning, we can go back to it. This type of, because with like in engineering, like we need to design things for, like it needs to have it needs to be safe, all right, it needs to have a degree of safety on it. So as you were mentioning correctly, now how can we go from uniaxial test, like having this parameters from this material in particular and use it to a global
Yeah.
validation scenario. Another important thing, super fast to
Yeah.
to to clarify is like, okay, behind this type of like, let's say, reasoning theory, it's important to highlight that we work depending on the code and depending on the approach. We would work mainly in the elastic region, all right? So
Mm.
depending on the philosophy on the code, and
Yeah.
then other codes will allow you to work in different areas. But commonly in piping world, most codes work within the elastic region, all right?
Yeah. Yeah.
All right, cool.
Yeah.
Continue, please.
All right. Thanks. Thanks. Yeah. No. Thanks. You know how to go from the stresses at one location in piece of piping to the code stresses. So typically, you know, you can think of that location and evaluate it using a cube, which helps you to you know analyze the situation. Let's say if you rotate the cube, you know you can analyze basically the stresses working on the surface of this cube for all different angles of rotation. And basically that helps you to build out more circle, you know, more circle with the shear stresses on the vertical and the
Normal
stress, the
strategy.
normal stresses on the horizontal. Exactly. If you do all those different angles for a 2D stress state, you would end up with that all points lie on this
You
circle,
will
more
find a
circle.
circle. Yes.
And from this circle, we define the principal stresses, which are these 2 points with zero shear stress, and we define the point of maximum shear stress.
Yes.
And then those 3 points for a 2D stress state um, are representable regardless of the orientation of the cube, right? I think that's something
Yes.
to uh,
Yes.
yeah take
Yeah.
away
So
here.
we start with the cube on an orientation that maximizes the normal stress, and basically, like, if you balance that cube orientation with the geometry, you will maximize basically let's say normal stress. And then you start rotating the cube, and it gets to a point where you maximize the shear stress, right?
Yeah,
You roll working with this too, and Morth would basically found that, okay, that described the equation basically for a circle, and we're able to on a chart establish where in the horizontal axis, well, the normal stresses, and then in the vertical axis the shear stresses. So the main goal is to compute, well, it is at some point to compute the maximum, like that point in particular, tau max basically.
yeah,
So
yeah, yeah. Well, I
good.
mean that's an interesting point. So Tamax, I guess it depends on the stress failure criteria that you're using. You know, that's what we're
Yes,
jumping into right now. Um,
evidently.
yeah. So, but like it took me a while, and that's something I would like to emphasize is that uh, like regardless of like from which angle you evaluate the stresses in a certain point, that these you'll always find if you know run through the equations of Mercer etc. You will always find the same principal stresses and maximum shear stress for that location. So those really represent the 3D stress state, I would say,
Yes,
at that location.
yes.
That's something really important to have sink in.
Another important thing they found out is like there's an angle where you can put your cube that it maximizes to being half, like you would have like this from actual, and then the maximum shear that you're gonna get is half. So
Yeah,
it is stated also in the equations, which is really interesting. Another important thing is that how, like, as you describe it really well, this, okay, they find out a way. We engineers at some point they did it amazingly, found out a way to represent the 3D states, the stress 3D state that you might have
yeah,
on whatever, and on whatever stress material that you might get on a metal piece of whatever, because this could be extensive to, we use it in piping world, but this is
yeah. This
extensive.
is generic. Yeah,
Yes.
yeah. All right. So then, how do you go from these values, principal stresses, maximum shear stress, to the
Oh,
uniaxial tension
there's
test?
also
Right.
another important thing to mention, though. Typically, can
Right.
you go back to Moore circle? So
Sure.
typically, we're working with two principal stresses, S1 and S2, because we're neglecting. So there's three of them, as we mentioned: radial, axial and hoop. And then we're working with two, and hence what I said at the beginning, that we can neglect in thin wall piping the radial stress because it simplifies the calculation. So
Mm.
here's an example of it. We have an S3. So we're neglecting because it says, okay, you like, it simplifies the calculation, but that will represent the third normal stress. So if you have calculations where the in case of working with piping, where you are accounting for radial stress, then you will have three principal stresses, which S1,
Yeah,
S2, and S3. All right,
yeah.
right, go on.
Fair
Go.
point. Yeah, yeah, yeah.
Good,
Going
good.
back and forth. I like it. Yeah.
Yeah,
So
yeah,
so
yeah.
then there's three basically theories that link those
Commercially accepted.
principal stresses and maximum shear stress to the graph shown here, which is from a uniaxial, with, evaluating stress in one direction. All right. Rankine theory, which is I think the most basic one, says, we'll just do a quick wrap up. If you want to really let this sink in, do the module and take some time. Failure occurs when the maximum tensile stress in the body, so in any 3D stress state, is equal to the maximum tensile stress in a uniaxial tangent test right at the moment of yield. So basically, it says, let's say the highest principal stress should always stay below the yield stress in this uniaxial
Yeah,
tangent test. So I've like, if you would visualize that in a plot, it would look something like a square. So let's say you have your
yeah,
two stresses, your two normal stresses, and the principal stress is at the edges of this square. You basically say, well, neither of the principal stress, whichever is higher, is allowed to go beyond the yield point, right? So
yeah.
so you'll end up with a square, I guess. Yeah,
It's basically longitudinal against longitudinal, right?
yeah, yeah, yeah. I guess so. Yeah.
Another
So
interesting thing, I think commonly in mechanical engineering is must work. These theories must work for fragile materials rather than
mm,
ductile materials. My
right.
understanding. Yeah.
Mm. Um, so things will get a bit more complicated if we use Tresca. That Tresca states something else rather than just taking the highest principal stress and comparing that to the yield stress from the uniaxial test. It says failure occur when the maximum shear stress in the body, so in any 3D stress state, the maximum shear stress in the body is equal to the maximum shear stress in a uniaxial tension test right at the moment of yield. So basically, you'll have to look at the definition, of this maximum shear stress and the equations behind that, and you have to evaluate what that would give for the uniaxial test right at the moment of yield, and then compare the 3D stress state of both. Um, and just a simple visual. Again, both principal stresses plotted against each other, and where the Rankine theory says this would bring a square, so you're safe as long as you're inside the square. Von Mises and Tresca theory will result in either, let's say, this oval shape or this, let's say, blocked
Yeah.
oval shape between them. Yeah. All right. Those stress failure criteria are kind of the missing link that will
A
typically
lot of
take some
people
time for
forget.
people to sink in.
So
And then,
another interesting thing. Oh, sorry. Like going back to the theory, which is important to highlight. Leave it
yeah,
there. Like three theories. So um, it is really amazing that several codes we would use either Tresca theory of, as I said, like working at least with metal, right? Like ductile
yeah,
materials, whatever. By the way, this only works so it doesn't work with orthotropic materials, right? Like you might have different.
yeah. Fair
So,
point.
so
Yeah,
hence, like we're working with carbon steel, basically. Well, still at least, right? And ductile material. So, which is important is like you to highlight is you would have codes. So most piping codes rely on Tresca theory, right? They
right.
use Tresca theory, which is important. Is like there's a balance to it. So when you
Yeah,
assess final
Tresca
result from the safety
like,
factor, yeah,
Tresca
there
theory is the
you can
block
leave.
one.
Yeah, you can leave that one right there because it explains a lot. The point, my point being is you for example might have B31.3, which uses Tresca to compute the stress levels, and then compare those against, as you were explaining, like, okay, I have my 3D stress state, and this is my will be my maximum value, and then I'm going to compare it to an allowable value. In this case, the allowable value will be based on either yield stress or ultimate tensile strength, right?
Yeah.
Which is interesting is like when you see it from that point of view, okay, you would have a theory that it's let's say giving you some results, and then safety factors that are higher for this type of criteria. And then there
Yeah.
are other codes. One, for example, is ASME Section 8, Division 2, Part 5, which it's
Yeah.
designed by
Yeah.
analysis that allows you to use vom misses. And which is really interesting is if you compare the safety factors, for example, between you would need to go to section 2 part D to find
Right.
these allowables. But
Yeah.
when you compare these allowables, one allowables might be meant to section 8 division 1, for example, and then section 8 division 2, for example. And then you might find that allowables for section 8 division 2 part 5 are less conservative, because
Yeah.
the theory behind it, or the reasoning behind it, is like you are doing like design by analysis, not by rules. So you're doing like a more tuned analysis, so it allows you to take advantage a little bit on the safety factor side,
Yeah.
which is really important, how that all that theory is applied to codes.
Yeah. Yeah. Does that? Maybe I'm jumping ahead of things a little bit here, but um, I know that for ASME A Division 2, Section 5, so design by analysis,
Part five.
um, yeah, Professor. So there's some for certain stresses. I mean, there's some yielding allowed as long as it is very locally, right?
Yeah.
Which causes a stress distribution. So yeah, I always I thought that was fascinating.
It
Just
will
to
depend. Yeah. So that's very, very, very interesting, because depending on your failure mechanism, also, right? We're
yeah,
gonna
yeah,
like talk about it in a minute, which is important. Like, for example, when you compare B again, like ASME B31.3 process piping code. There you might have allowables for primary stress are based directly on yield stress. I mean, if you're not in creep range, all right.
yeah, yeah.
When you're not in creep range, you would have an allowable based basically in yield stress and ultimate tensile stress. All right.
Right. Yeah.
But that will be for primary stress, right? That you would define, okay, my sustained stress should be less than 2/3 of the yield stress,
I
or
think I have
one.
that open actually. Give me a
Yeah,
second. Yes, this one for B
yeah.
31.3. Yeah.
What I'm saying with this is, like, for example, if you compare that criteria, because with occasional stresses is the same, you're applying 1.33 or 1.2 times SH, which will be your allowable based on yield stress and ultimate tensile strength. But if you check, for example, it's really important to highlight that if you check displacement of stress range, if you check equation 1A and equation 1B from B31.3, and you
Right.
do the math, trust me on this one, that's a homework for you guys. Like, if you do the math and you're using, for example, equation 1b, which is the famous liberal equation from Caesar 2, well, it's the equation from the code. It's an option you have to select in Caesar 2 to take
Yeah.
account for that. It allows you to have a small, like, it would allows you to get to yield
Oh, it does.
in displacement and stress range, yeah, which is really important. Not many people know this, but when you and it's done. We're going to talk about it in a minute. It is related to elastic equivalent stress we were talking about earlier.
Yeah. Yeah.
But it that actually the equation for SA, which is your allowable stress for displacement and stress range, we will give you under certain conditions. It would allow you to get even to yield, or even a little bit upon yield.
All right, all right. Let's jump back to the main storyline, and then we'll go into more detail there. So if we go from these stress criteria, stress failure criteria, and we would fill, in the details. And for example, if you look at maximum shear stress, if you look at the equation itself, with the square root, and then there's a square in there. This looks a lot like Pythagoras, obviously. Um, it already looks something like what you can see in the code, which is shown here at the bottom. The
Yes. Yeah.
displacement stress range. This is from the B31.3. Displacement stress range is equal to, and there we again see this square root, and again has this look and feel of Pythagoras theorem. Um, you pointed out a very true typo in this sheet, which is basically that in the code it doesn't say tau, but it says the stress. But
Yeah. ST.
that's a mistake from my end, which is solved in the Spanish version. So for those Spanish-speaking
It's
people,
not a mistake. It's a
it's
typo.
improved.
Right?
Um,
But the
so so
reasoning, yeah.
well, basically, here we see the link from everything we discussed. Going from the uniaxial stress test and then the 3D stress states, and we fill in all the equations for the principal stress that we find if we do the detailed calculations,
Yeah.
which are shown in the videos. And if you actually fill it in, you'll end up with this equation, which is the same. The symbols are a little bit different, but it's the same representation as the displacement stress range. So
Yeah.
that links everything together, which is basically what we wanted to
Yeah.
highlight here.
If you would like to take a deep dive into that, it is in one of our videos. I think is the last video.
Yeah, yeah,
We
number
explain.
10.
But
Yeah,
basically, what is happening there is like we grab the Tresca theory, replace the principal stress with the corresponding stresses, and you do the math. To simplify things, we basically use the safety factor, introduce the two into the other side of the equation, and you end up having that particular equation. Which, by the way, another fun fact is this typo. I wouldn't call it a mistake; it's a typo. Okay, but it's basically so in B31 world the stresses are called S, right, with S's, right, and then
exactly.
in the European code in EN the stresses are more familiar to with the stress theory, calling tau normal stresses, sorry, calling sigma normal stresses and tau shear stresses.
Yeah,
So
yeah,
yeah, but in
yeah,
the code you will find it as ST. But yeah, that's one of the examples of the greatest examples how you are able to coming from the theory. And this is why I call this amazing course Pipe Stress 101 to me. It is the very core of it that you're able to see how coming from the theory and doing all this reasoning behind, you get to the equations that in fact are used in the code. That
yeah.
is the same thing with Barlow's equation to compute hoop stress. Like actually, there's a version of over PD over 2T, basically. So yeah, everything, yeah, it has a reason, which I found really interesting for young engineers or every single engineer that works in piping, and I think it's a must to know
Yeah,
that.
yeah,
Yeah.
yeah, I agree. Like, and as I said, it took me a while to grasp this process when I started. Um, let's just I mean that's for all I think we should cover for the free module. Let's just jump to some questions, Geronimo. And I mean, we're already running way
We'll
you know
do a
we're
rapid fire type
running
of.
late. Well, I mean, I think we're having a good conversation. So let's just continue for a little more. So one of the questions we get, like everybody asks, right, is why do you differentiate between displacement stress and sustained stress, right? And this primary and secondary stresses. Like, why do we even do that? What are the concepts behind it? What is your take on those things? Because here in the slide it says the displacement stress range, which is obviously um, related to secondary stresses. What is your take on this topic?
Yeah, so there's several factors to it. Like, if I describe it as a puzzle, there's several pieces of it. One would be the failure mechanism that is present
Yeah.
and whatever you're evaluating, right? So to give you an overview, so they're depending also on the code though. I mean, like previously, I don't know, it was removed. I don't know how many, I think it was in the 2014 version of the code, but back in the day we used to have appendix P, which was
All right.
developed by Mr. Chuck Batch the fourth, the brilliant mind behind it. So it was a kind of type of a stress where you were able to include like primary stress and secondary stress on it and have allowables to do so.
All
But
right.
the reasoning, yeah. So also you could have, like, for example, in the European code in 14380,
Yeah.
you would have the way it assesses creep range, creep stress. It's really kind of a scalar way to compute a stress when you're mixing basically sustained stresses with expansion stresses,
All
which
right.
is really interesting. But I would call it well, I wouldn't call it. It's called that way. The base code of B313, for example, it splits it in what will be primary stress and secondary stress. So primary stress will be force based, and then
Right.
secondary stress will be fatigue based, but with low
Yeah.
cycle fatigue though. If
Yeah.
you're
Yeah.
if you like have high cycle fatigue, then you have another chapter to go, and then you could assess it there. All right,
Yeah.
but
Yeah.
what's really,
So just to summarize, like the first piece of the puzzle, and that's, to be honest, the piece that I thought of when we discussed this question earlier, is you need to separate them because you need different allowables, and in order to evaluate the different failure modes behind them. So you need a different allowable for primary failure than you do for secondary failure, and even a new one for fatigue failure. So that's one of the pieces to the puzzle, I would say. You brought a second one to the
yeah,
table
yeah,
as
yeah.
well,
So,
I believe.
yeah. So it's all connected, right? Like it's like your failure mechanism, and then it will be like summed up as a, you would have your self-limiting stress, and you will have your non-self-limiting stress, and that's
Right.
the key behind the thing, because every force-based type of stress is non-self-limiting. That
Yeah.
means
Pressure,
your stress,
gravity.
yeah, that means that your stress won't stop, like it will continue, like if you allow it to, it will
Yeah.
continue until it breaks, right?
Right.
And
Yeah.
then the reasoning behind it is like, if the other side of the puzzle is like the material itself behaves differently. So if you analyze this type of stress strain kind of curves, you will get that for primary stress, like if you assess it from a primary stress point of view, you will end up having one stress strain curve, and then if you assess it for a self-limiting kind of load on it, you will get different results. And
Yeah.
what happens there is that in the curve, the strain is increasing in self-limiting stress. All right, the it would increase but slowly, so you will have a big region of stress being close to the yield stress. All right,
Yeah. Yeah.
so that changes everything, because the material won't behave the same way when it's being subject to self-limiting stress and when it's subject to non-self-limiting stress.
Yeah.
So
I would also like to add that most equations, linear type equations, most pipe stress software packages, etc., they just assume that they're based on Hooke's law, right? They
yes,
they
yes,
assume they
that's,
just shoot straight
yeah.
up.
That's highly important. That's the definition of the elastic equivalent stress, which is basically, if you allow me to explain it, is so what happens there is that the actual stress of a self-limiting stress rarely exceeds the yield strength. All right. So
Yeah.
the self-limiting stress is evaluated. So what we're doing is evaluating the strain rather than the stress when we're talking about displacement and stress range,
Mm.
which is a self-limiting type of stress. So every software traditionally it's set up to calculate stress by the elastic method. Then the elastic equivalent stress is used to measure strain. So what you're computing basically is a strain. So you're controlling strain displacement.
Yeah.
Then the elastic equivalent stress basically is the product of the strain and the modulus of elasticity, replacing the actual stress strain curve, which is a straight line that extend from the initial stress portion, so the elastic region of the curve.
Yeah.
So
So
yeah, that
basically, if,
yeah.
let's say, you would have a primary load and you're analyzing it, and you find a stress of 400%, and the associated strain or displacement is relatively high as well. um, I mean, that strain especially is not both numbers are not realistic at all. Like the software just assumes that it just goes straight up, right?
Yeah, so the equivalent stress can be several times higher than the yield stress,
Yeah,
yet the actual stress is still the same as the yield stress.
yeah, yeah,
That's what I'm trying to say. So when
yeah,
you're, for example, if you're extending this line, so you get a failure of a 400%, for example, that's not real. What you're doing is controlling your displacements, controlling your strain. So
yeah,
in every like common typical pipe stress software, like what you're doing, it uses this definition of elastic equivalent stress. So what you're doing is when you're staying, and that's why you should know, that's another safety factor, that when you're doing that, what you're doing is controlling your displacement. So you're designing for the displacements. that's
yeah,
that's why it also lets you to get super close or even pass a little bit the yield stress,
yeah,
because at that point stress is not relevant but strain.
yeah. It will
Yeah,
simply
yeah,
stop straining. Yeah.
yeah. All right,
Yeah.
cool, man.
All right, yeah, let's wrap things up, Geronimo. We've been going for a good 50 minutes now. For all those listening, like first of all, we mentioned a few courses. The free pipe stress foundation, the free thin versus thick wall piping, and the full pipe stress analysis program. And we thought it would be nice to wrap up simply with some recommended books as well. Oh, I
Yep.
have the wrong one. Give me a second. There we go. And these ones were books that you brought to the table, Geronimo. So
Yeah, I
maybe
would
you
like
can take
also
the lead.
to, yeah, to the audience, to that's one of the key books, I would say, my recommendation of key book that I found during my career very helpful to read.
Hmm.
I You allow me to, I will give you a recommendation to read these books, all right?
Yeah, no,
Because
sure. We have
yeah,
which ones? We have this one.
yes.
I actually have them here. I found them.
Yeah,
Yeah,
yeah. So
pipe stress engineering, process piping.
yeah, so so don't jump right into the pipe stress engineering because that will be more complex. So my recommendation would be go to Introduction to Pipe Stress Analysis by Sam Kanapan. All right, because it is a really interesting book. It's an Indian guy that is a brilliant mind that basically lays out all the information, very very well put it, and it's good to start at that point, and then you should jump right into the pipe stress engineering made by the like mastermind of LC Peng
All right.
and Sen Long. That book, to be honest with you, changed my life. I've read it, to be honest with you, more than 4 times, and every time I read it, I
Oh,
find
that's
new stuff. It's amazing. I recommend it. And
wow.
then if you're a geek like me with the codes and process piping and power piping, whatever, then I would recommend the book from the Dr. Charles Batch, Chuck Batch, which is yeah, I mean, they're from the code. He was a very important person in the piping world and in ASME, which is the process piping, the complete guide. There's two books. Like if you're more from the power piping world, there's the power piping, the complete guide to ASME B311. And if you're a
Mm,
process guy like me, like a process piping guy like me, then there's this version of the code, which is process piping, the complete guide to ASME B313.
right,
Those
right.
are my three topics, top picks for you to read in your career at least once. That's a personal recommendation.
At least once. You went 4 times at it. All right. I can't say I did. I did the same. But
It's,
all right. Thanks for sharing, Geronimo. I think that's good fun. And let's leave it at that. It was a pleasure to connect. I mean,
always a
lovely
pleasure to be
conversation.
here, man. Always a pleasure to be here.
All right, and I hope from you listening at home or from work, you enjoyed this conversation. If this type of content is relevant for you, make sure to subscribe to the YouTube channel and also check out these courses. Several are free. You can just go straight at them, and perhaps one of the premium courses is relevant to you and your team as well. Having said that, Geronimo, thanks again. Have a great day. Have a great day for
Thank you
all
so
of you
much.
watching.
Bye.